Welcome to the 15th class meeting of Introduction to DSP. You will have the homework as usual. We are covering chapter 4 on sampling of continuous time signals and its applications. There were so far 4 messages. First one was that whenever you see a mathematical formula, try to verbally express it. That may give you new aspect and that will make you easy to remember the result. When you use LLMs these days, be careful about the hallucination because exact opposite answer the LLMs may generate. Third one was the most important because these days students rarely read textbooks. So please read textbooks and other reference books or even Wikipedia in order not to become a degraded copy of your professor. And the last message was, whenever you need time, just stop and think. It's not costly. Stop and think will give you more profit. Here goes the review of last class meetings. So we were basically studying 2 things. What are they? C2D converters and D2C converters. Here, these are mathematical models. So we have continuous time signal in, discrete time signal out, and discrete time signal in, and continuous time signal out. And there could be many, many such transformations or systems, but here in this chapter, we consider uniform sampling. So in the time domain, x of n is defined as the evaluated version of the input continuous time signal for all n. And in the time domain, this reconstructed signal can be represented as a interpolated version. Let me use P. Interpolated version of the discrete time signal. Here, P of t is called interpolation function or waveform. And if it is the impulse response, then it's called filter impulse response of the filter. Various names can be used. And the question was, what's the relation in the frequency domain? So what does that mean? The DTFT of x of n, can it be written as in terms of the CTFT of this input? And here, the CTFT of this reconstructed signal, can it be written as the DTFT of this input discrete time signal? And in both of the problems, we have a trick. So before we talked about the main result, we had so-called 2-stage representation. Anybody remembers? So instead of just defining as the output as the evaluated version, the authors of our textbook and many people have the standard approach to divide this C2D converter into 2 serially connected subsystems. So here goes the continuous time signal in, and you multiply so-called sampling signal or sampling function, which is basically equally spaced delta functions with spacing t. And here goes your continuous time signal. This is very important. Your continuous time signal is then processed by modulated impulse to discrete time converter to have xn. So simply the textbook says impulse to dt signal. What about D2C converter? For the D2C converter, we have almost the same thing. So here goes the input DT signal. And you have DT signal to impulse trains, modulated impulse trains. So you may have x sub s of t. And then here is the interpolation filter. With impulse response p of t. So you have y reconstructed of t. Let's see this y sub s of t carefully. Here you have y of n times delta of t minus n t I. By the way, let me distinguish these two. So t sub s is called the sampling period, or sometimes some people use sampling interval. And here ti is interpolation period or interval. And their inverses are called the sampling rate, interpolation rate, or frequency, some people. And in practice, both of them are often in these days has the unit of something like this. Mega samples per sec. So MS capitalized and lowercase s, MSS. Sometimes this interpolation rate is called conversion rate. So you'd better remember these two, sampling rate and conversion rate. These days, both have mega samples per sec, or if you want kilo samples per sec, something like that. So you have exact parallel here and there, but there are a slight difference. So explicitly, here you have impulse trains, but there is no unmodulated impulse train here. And we used these two-stage representations of C2D and D2C converters to derive the frequency domain relation. And I'm not going to review that part, and you do it. It takes too much time to rederive. Got it? And today, we are moving to section 4.4 and 4.5, where we use C2D converters C to D converter and D to C converter at the same time to do something good. So here in section 4.4, entitled DT processing of CT signals, the story is like this. You have continuous time signal, and here goes C to D converter, and you have discrete time signal processor, and here goes the D to C converter, and you have output. And here in section 4.5, you have something like this. You have a discrete time signal. It is first converted to a continuous time signal. And here goes continuous time signal processor or some analog circuit. And you have C to D, and you have Y open. Got it? And you may say that, what's the use of it? It's very useful in many cases. And the use of these approaches appear in many places, even in this era of AI ML models, right? So if you join, for example, some circuits lab, they will say that, hey, you do the research by kind of converting your neural net, mostly implemented using digital systems, to some analog systems. And you may wonder why. And they say that because of this, because of that, something like that. Got it? So I believe mostly we will cover sections 4.4 and 4.5. But before we move to that, actually, there are many things to emphasize. So let me take time before we move to this section 4.4 and 5. Actually, these two sections can be easily understood even if I do not say anything. Because you learned what is C to D converter and D to C converter, and how you model mathematically these two systems, and what's the relation in frequency domain. What is more important is actually a little bit more in-depth understanding of the sampling theorem. So I've decided to talk a little bit of mathematical analysis stuff related with the sampling theorem. So here goes the notion of convergence of a sequence of functions. So as it says, you have a sequence of functions. Have you ever seen an example? Once I told you, if you truncate the Fourier series up to some nth order, then you have a sequence of functions. So just consider some x sub k of t. Here, k is the index of the sequence. For simplicity, let me use just natural numbers for the index. And here, the convergence of a sequence of functions will handle something like that. Here goes the definition. The sequence let me not use this because it looks more like a set. So let me use parentheses, even though there is inside parentheses. The sequence of functions converges to some function, right? If blah, blah, blah. And anybody want to fill this part? And whenever you are asked such a question, you have to do what? You have to search something similar in your brain from the first cell to last cell in your brain. And anybody? You've seen something similar like this. You have, for example, a sequence of real numbers. Let's say xk. Got it? So the only difference is that here you have, for each index k, you have a real number. And here you have a function. And what was the definition? Converges to another real number, right? If what? You want to say something like this, right? But actually, this is not a definition. This is a notation in Korean 표기법. Then what is the definition? And that part is not taught in your high school, even though you solved a lot of math problems related with the limit of a sequence of real numbers. And what was the definition? And you learned in your college level calculus. So for every epsilon positive, there exists n, which is determined by your choice of epsilon, such that n greater than n of epsilon implies xk minus, just a second, kn. Okay, let me use n then. It's very confusing to use. Okay. Yeah. Got it? So this is the definition. So you may want to just extend this idea to define the convergence of a sequence of functions. That is one way. So let's do that. For every epsilon positive, there exists n of epsilon such that n greater than capital N of epsilon implies, so here x of, let me replace n. Yeah. So n of t minus x of t less than epsilon. So here you suddenly notice that something's wrong here. What is wrong? Because as I told you, when you have a parameterized equality or inequality, how many equalities or inequalities do you have? I'm not talking about n, I'm talking about t in this case. So if you choose t in the domain of these functions and the limit function, and suppose t is an interval. Even though it could be a finite interval, you may have uncountably infinite real numbers from A to B. So how many inequalities do you need to check? Right? So something strange, but people decided to just ignore and define the first thing. Okay, I'm not going to repeat this one, but let me use this notation. So they decided to have the first definition. Okay, limit xn of t equals xt, and these are functions, and functions are equal if the values are equal for every possible xt in this case, right? So this could be a definition, right? So if you choose a t in the common domain of these functions, and we assume that you have uncountably infinite possible values of t's, so you have to show uncountably infinite convergence of sequences. And some of you say, what? And let's consider that famous Gibbs phenomenon thing. So suppose you have a periodic rectangular pulse. And you find the Fourier series. And let's say this x sub n of t is what? The truncation of the countable sum from negative n to positive n. Then what happened? You had something like this, right? Depending on the order of n, you may have more close function to the original periodic square wave. Now, recall these figures in your undergraduate signal system textbook, and let's think about what is the meaning of this one. So since it's periodic and your Fourier series also has periodic summoned in the summation, you have to think about, for example, a single period of t. And in this period, how many possible value of t's do you have? Uncountably infinite. So what you want to check is this one. So suppose you choose this real number, say t0. And at that t0, what do you have? If you replace this to t0, this value now becomes a real number for each n and t0. So on the left-hand side, you have a sequence of real numbers. And on the right-hand side, you have x of t0, which is a real number. So you can use this definition. You have a sequence of real numbers at each t. And you want to check whether that converges to the original signal evaluated at the same t0. And you do this for every possible t inside that one. And if every possible t satisfies this equality, then you want to say what? Everywhere. Everywhere in the domain, actually. And this is the first definition. So convergence everywhere. Definition. Got it? So convergence everywhere is very simple. You just view a sequence of functions as uncountably infinite number of sequences of real numbers. And each sequence converges to the function evaluated at that time. Got it? So this is everywhere convergence. But as you know from this Gibbs is the name, not Gibb, Gibbs. So the Gibbs phenomenon. What do you remember about Gibbs phenomenon? Probably you remember this one. At this discontinuity, this amount of overshoot and amount of undershoot, the maximum overshoot and undershoot amounts does not vanish. Here, vanish means disappear. Even though you increase the terms to infinity, to arbitrarily large, okay? You choose 10 million. You choose 10 million raised to the 10 million. Even if you do that, even when you do that, the amount of maximum error does not reduce. And here, at this, let's say this is some t0 of discontinuity. So if you evaluate that one, the Fourier series, what you find is very interesting. What was that? You had the average value of the right limit and left limit. So if the height is 1, then you had 1/2. Got it? So your left-hand side does not converge to the right-hand side. And on the right-hand side, of course, you may have defined the value is 1/2, but probably you used this value or that value, 1 or 0. So what you remember is that not only this example is important, showing Gibbs phenomena, but also it's very important in that the left-hand side converges to the midpoint of the right limit and left limit in this case. So if you haven't defined the value as the half, then what happens? This everywhere convergence is not satisfied by this periodic signal. Let me repeat. Usually we love electrical engineers write continuous function. So something like this. So here, the original x at t0 is what? 0. But your left-hand side converges to half of it. So at these points of discontinuity, you don't have this convergence of sequence of real numbers. But we know as an engineer that, hey, this single point, actually not single point in periodic, so we have countably infinite number of non-convergent points, but we know that as told you, what is important in our mathematical modeling is the signal energy or signal power, depending on whether we handle an energy signal or a power signal. And we know that these points do not contribute to the amount of energy or amount of power. So it's not that important. So people define the second one. Hey, okay, so let me think about a set of points. So T in the domain. I'm assuming the signal, each element and the limit function has the same domain for convenience. So you try to find where the limit of a sequence of real numbers equals the limit. So this set does not include these points, right? In this example. And what we want is that the complement of this set has, this part is very confusing, measure 0. And you may just regard it as a length of a set. So as you know that this interval AB, we all believe that they are of the same length, B minus A. So we ignore the endpoints, whether they are included or not. Similarly, it's not exact, but similarly, if this set where the sequence of functions does not converge to our target limit function has length 0 or measure 0, then we say it's okay. And we call this as what? Convergence almost everywhere. Got it? The problem is that convergence almost everywhere seemingly useful for engineers and scientists, but they have found that it's too restrictive. So people have defined another one. It's more, how to say that, engineer's idea. So here goes the third definition. And we know that what is important is the energy. And whenever we use a sequence of functions, actually we are not mathematicians. So what we want is that, hey, for sufficiently large value of n, the function is close to the limit function. That is what you want, right? So for sufficiently large n, we want to say something like this, right? As an engineer or scientist, what would be important? There could be many, many different definitions, but people have devised an interesting definition, and it's very simple. So they subtract and take the error, absolute error, raised to the power of 2, and then they integrate over the domain of these functions. And let me see, what is this one? This could be error parameterized by n, right? For example, in this periodic rectangular function approximated by Fourier series, truncated Fourier series, this function E sub n is the difference between the nth approximation and the, for example, original periodic signal. And what do? You compute the energy of the error signal, right? So this is what? This is the energy in error signal. And now, what do you want to say as an engineer or scientist? You may say that, hey, this is almost 0 for sufficiently large n, right? By the way, in many engineering and science courses, they love this for even they use just f dot, okay? And what does that mean? For sufficiently large n, right? For sufficiently large n. Of course, your friend in math department will hate it, so we will little bit modify and say this one. Now, let me ask you, in this equality, how many equalities do you have? You have one. Because here, this is what? This is a scalar. It's not a function of t any longer before you have integrated with respect to t, right? So basically, on the left-hand side, you have a sequence of real numbers, non-negative, right? And this sequence of real numbers, we want to converge to 0 as n tends to infinity. By the way, n goes to infinity. Some people love it. N tends to infinity. Some people, n converges to infinity. Something like that. And it means the same thing, right? At n goes to infinity. And this real number sequence converges to 0. What does that mean? Now you know, as a student taking this course, though some sequence of real numbers converges to 0 must be interpreted as an engineer How? For sufficiently large n, your sequence element is very close to 0, right? Got it? So in this case, energy in error signal is small enough, ignorable if n is large. So it really makes sense and appealing. So people have the third definition, convergence in mean square sense. Why is mean square? It's a little bit complicated, but anyway, it's related to the expectation and square. So this, but they have generalized for p larger than 1, any real number p larger than 1, and they renamed this convergence as convergence in the pth mean. Or some textbook says in LP, convergence in L to the P, something like that. Got it? So here the energy in error signal goes to 0 is what? The case with P equals 2. You can use any one. The problem is that sometimes people have found that this is too much, still too much. By the way, this third one is what we are going to use when we talk about the sampling theorem, Nyquist sampling theorem, not the Shannon sampling theorem. Because in Shannon's sampling theorem, we handle a random process. So we don't have a sequence of deterministic functions. In that case, we have a sequence of random processes. So definition apparently looks similar at the first glance. They are different. And actually, Shannon's theorem is much more profound in the sense that it talks about the convergence of a sequence of random processes. Got it? Anyway, so I'm not going to talk about that. The fourth one, which is also useful, is the convergence in measure. And the idea is like this. So we know from the idea of almost everywhere convergence, we want to take the set of t, the time, where the error is greater than epsilon. So it's like, in this example, you choose some epsilon positive, and you move that interval plus epsilon and minus epsilon with the reference to the original periodic function, and check at some point t, this approximate signal goes out of the boundary, right? If you choose epsilon too large, every t in the domain will be included less than epsilon, included inside this set, right? If you choose epsilon small enough, what will happen to this Gibbs phenomenon related periodic scale wave? Probably around these points of discontinuity, you will have uncountably infinite points that deviates from the original scale wave by the amount of plus minus epsilon, right? Of course, if n is large enough, what will happen? those lengths of the set would be very small. So just consider fix epsilon and n and think. Then you have some interval here, there, right? Will not be included here. If you flip the inequality, then these points will be included inside this set, right? Now, we want to combine this idea of the set of points where it deviates too much from the limit function, becomes smaller and smaller. Probably what we want is to take the measure or length of this set, and we want to say what? This equals almost 0 for sufficiently large n, right? So what do you want? You want something like this. For every epsilon positive, the limit of this set equals 0. Got it? See that? You choose some epsilon. Then each n will give you a set. Now it is converted to a number, length. So for each epsilon, for each epsilon, you have a sequence of real numbers. And whatever epsilon you choose, you want what? The sequence converges to 0. So here, how many sequences do you have? Uncountably infinite sequence, right? So the definition is a little bit messy because you have uncountably infinite choices of epsilon positive. But people have found that sometimes this definition is enough. And this is too strong. And they try to find the relation between these 4 definitions. So convergence everywhere will be abbreviated by E dot. And A dot, E dot means almost everywhere. In the piece mean. And here in measure convergence. They have found something very interesting. Of course, everywhere convergence implies almost everywhere, right? And you have these implications. So if you have everywhere convergence for a sequence of functions, it not only almost everywhere converges, it also converges in measure. If you choose some p and show that p, for example, 2, and it converges in that second mean, then automatically it converges in measure. Good, right? Sometimes, depending on your application, sometimes proving this one, so your sequence of functions converges to another function in measure may be enough. Sometimes this is enough, but it's like this. You wanted to prove that one, and actually proving this one sometimes is very complicated. Sometimes, not always. Usually this is easier. But this is also, in many cases, not that difficult because it handles only a single integration. Of course, it's a sequence of integrations. Got it? Here goes the final thing. Relation with sampling. So I'm not going to prove that, but let me give you the exact theorem. So here goes the Nyquist sampling theorem. For perfect reconstruction, given a finite energy signal x of t, the sequence of sequence of functions defined as let's use this. Converges to x in the mean square sense if blah, blah, blah. Got it? And you may say then, what? So what is this one? What is this one? X of n of t is the approximation of the original signal x with only 2n plus 1 samples interpolated by the sinc function for the sampling rate t. So here, the sampling rate and interpolation rates are matched, right? And of course, this signal is in general not equal to x of t. But you know that if n is sufficiently large, and as an electrical engineer, we know that this time sample can never go to negative infinity and positive infinity because of this theory of Big Bang, right? And the invention of electrical engineering by human being after some 16th century. So here, let's focus on what does this mean using the previous definition. So it's like this. We integrate over the entire interval, and here goes our original signal to be sampled, and here goes our approximated interpolated function. And only 2n plus 1 terms are here. And you calculate what? The error energy, right? And for sufficiently large n, if this error energy is small, then we are happy, right? And this makes sense to us electrical engineers, right? If you define the time origin t equals 0 for your interest, then probably those samples around that time period are important. And some 30 years ago, your system never existed, so there is no signal. In even 2 years, I will replace this one to a new Galaxy S20 something, right? So there is no signal. So if this is small enough, then we are happy. So we have mathematically this one. So what is the Nyquist sampling theorem? It's a special case of a sequence of functions converges in the mean square sense. Got it? That's what I want to say. Of course, depending on the signal's property, sometimes you can prove more stronger version of convergence, such as what? Almost everywhere convergence or everywhere convergence. Or depending on something, you may have sorry. Actually, these are, let me retract, because they don't in general have implications. So let me retract that stronger version. Let me just say that you may prove some other versions, different criterion definition of convergence. But for this one with p equals 2 are in many cases, not always, are very appealing to us electrical engineers. And the most well-known version of the Nyquist sampling theorem, very mathematically rigorous, is related to the convergence in the mean square sense. Got it? By the way, this part you already know. If signal is strictly band limited and the sampling rate is greater than or equal to twice the highest frequency content, then blah, blah, blah. Got it? So I'm happy, and I believe you are also much happier than before about the definition related to the sampling theorem. Got it? So mean square convergence, right? And error energy, and for perfect recurrence. So here, perfect means what? Perfect does not mean perfect. Perfect in the mean square convergence. Got it? So for sufficiently large n, error energy is small enough. In that sense, perfect reconstruction. Okay, I have around 20 minutes. And let me be very, very quick about sections 4.4 and 5, because they are not that difficult. It's just you know the two blocks. You have two Lego blocks you played with for a long time that then you just combine. You just need to know this approach is very, very useful and very, very omnipresent everywhere. So here goes continuous time signal converted to a discrete time signal, and here goes the processor, discrete time signal processor. So output is discrete time signal, and it's converted back to a continuous time signal. And one of the most important example is what? CD player or your MP3 player or something. You record your voice, and you store and you process denoising, filtering, some tuning, and then you play back. This is the idea. So here goes the C to D converter and D to C converter. You already know. Be careful. Here you have what? Sampling rate. And here you have interpolation or conversion rate. The simplest case, in the simplest case, you have the rates the same. But depending on your application, they are not necessarily the same. So let me emphasize by writing this T sub S sampling period and T sub I interpolation period. They could be different, but in many undergraduate books and exam problems, it is just simply assumed they are the same, but that's not necessary. For your convenience, you may change. And by the way, this kind of revolutionized electrical engineering. Before, the audio players, such as cassette tape, Walkman, Sony Walkman, the Korean companies like Samsung or LG could never beat their quality. Because at that time, it was mostly analog component-based system. And usually we, the young, at that time, young electrical engineers kind of was very hopeless state, like, hey, Sony has so-called masters 장인, masters in audio signal processing. They are 65 years old, but they do some tweak and the noise goes out, disappear. But we don't have, we can never beat the Japanese electronics companies something. And when I was at your age, our newspapers said every year that the gap between Japanese electrical and Korean electrical manufacturing companies, their gap widens. And at your age, I even sometimes thought that, hey, it seems that Korea is hopeless. But suddenly it changed. Probably you don't remember, but the first company who mass produced the MP3 player was a Korean company. So actually, Koreans invented the MP3 player. If we say Steve Jobs invented smartphone, he never invented smartphone. But people say that. Now, then, why not? We just celebrate that MP3 player was invented by Korean. And Korean engineers have exploited this approach. So they found that C2D converter and in D2C converter, there is not much thing to interfere. And they put every processing. Before that, the Japanese masters in analog circuits was doing, we put it here. And suddenly, it was really amazing. Suddenly, when I purchased the Korean company's audio, there was no hissing noise. I was shocked. And we could sell these products because Korean companies did this. Okay, so digital signal processors are here, as I have drawn here. So in real world, you have block diagram like this: A to D converter, analog to digital converter, and digital signal processor. And you have D2C, D2A converter. This revolutionized. And more analog components are now moving inside the DSP. So even the radio transmitters and receivers, they are removing more and more RF components. And more RF components are now, their functions, mathematical functions, are performed in digital part. And in digital part, we can do a lot of interesting things, such as OFDM, for example. Many of you may have taken communications course. And in OFDM, with, for example, 600 subcarriers, is it possible to do OFDM using analog components? You may need 600 local oscillators whose phase are perfectly synchronized. And it just simply seems impossible. So what's going on? We do digital signal processing. Especially, we use fast Fourier transform. As I told you, the core of this course is related to the discrete Fourier transform and its fast algorithm named fast Fourier transform, right? And actually, fast Fourier transform is used in sort of 600 oscillators. And it's amazing. And your cell phone, 4G and 5G, both has these oscillators virtually by using DFT implemented using FFT algorithms. Okay, anyway, so why do we do that? Why do we do that? Because of the evolution of digital signal processors. Got it? The problem is that for this one, mathematically speaking, in order to have the same information here and there. What do we need about this one? We need this signal strictly band limited and our sampling rate greater than twice the maximum frequency content. What if that is not met? So let me move far away. Where it is? That is probably covered in section 4.7, so I am not going to tell. But anyway, so in reality, what we have is that we have a baseband filter. So sometimes if our sampler or C2D converter cannot sample fast enough, we just cut out some energy, discard some power of the signal. That may sometimes seriously degrade the quality, but the C2D and D2C, which corresponds to the ADC and DAC, they are also becomes very, very fast. So in most of the cases, that is not a problem any longer. But long ago, when I was at your age, and I made a phone call to my, for example, uncle in the United States, the voice was always like, "Hey, uncle, I'm Juno. How are you doing?" And he said, What? Something like that. Because of the high frequency components were just cut off. Because most of the information is in the low frequency part. And people, the telephone companies, wanted to reduce the bandwidth. So they cut out the high frequency part. So sometimes if I pronounce consonants, 자음, not 모음, vowels, then it was kind of hard to hear. It's like cha and ja couldn't be distinguishable sometimes, right? So we had a lot of trouble. Anyway, so why do we do this? Because of the revolutions in the A2D, D2A, and DSP. And that is the direction towards the future. So this part is very important. Sometimes people have found that it's very easy to implement complicated analog system. So for example, this entire block can be viewed as a continuous time signal in, continuous time signal out system. Apparently, it looks like that, but in reality, what happens? C2D, digital processing, and D2C. So as I told you, the electrical engineers are, how do you say that? Applied mathematicians. We use mathematics and find some equivalent approaches. So continuous time signal in, some processing, discrete continuous time signal out. But we have found that, hey, if this signal is band limited enough, then let me sample it. So DT signal, digital signal processing or discrete time signal processing, C2D, and the output is almost the same. And these digital processors and A2D, D2C converters are evolving very fast, very low cost, very low energy power. Let me do this. That is the idea. Got it? This part, you read it. It's not that difficult. It's the application of signals and systems and what you learned so far. Low-pass filtering can be done. Analog low-pass filtering can also be done by doing this DT processing of CT signals and some other things. Even some differentiators can be implemented using this one. Because differentiator, which differentiates the continuous time signal in and generates the differentiated version, actually, if the input signal is band limited enough, then effectively we do this in the analog domain. So what we do is that our discrete time signal processes this way. Then it's much easier to implement. And you may say, why? But differentiation is related to, in your basic circuit theory, is related to the inductor if we want to generate, right? If we want to. So current in, and you differentiate, then voltage out, and that is the inductor, right? And inductor cannot be easily implemented in 2 dimensions, right? It's a basically 3-dimensional something. But if we want to make it very, very small, what do we do? Of course, we can wind that wire very small, but this cannot be miniaturized. We don't want very bulky system. And we do what? Digital signal processing. Now, I have 10 minutes, 4.5. Now, we have almost exact opposite. And when I was at your age, this was stupid at that time. And I just ignored this entire section. Hey, just for symmetry, okay? There is a DT processing of CT signals. So mathematically speaking, there should be CT processing of DT signals. And whenever I thought that, it turned out in less than 10 years, it was a very naive idea. And anyway, here goes the block diagram. So you want some discrete time system that processes a discrete time signal and generates a discrete time signal. But sometimes we use D2A converter, and we have some analog circuitry or something equivalent, and then we sample and generate the output. Anybody knows the example? The textbook says non-integer delay. You read it. It's not that difficult. But let me tell you some other cases. Where are they? Yeah, so resampling at non-harmonically related rates. What does that mean? So actually, the textbook says this one. So it's like this. Suppose this original signal was sampled version with rate t. Got it? But now, what you want is that you want something like this, right? Just for convenience. So your DT signal is actually sampled version of an analog signal with sampling period t. But you found that, hey, I need square root 3 times t needs to be a sampling period. Then what do? One way is what? You convert it back to a continuous time signal, and you resample to have that one, right? So it just makes sense. By the way, you may not be familiar with harmonically related, but just think of it as a kind of rational multiple or something. So, for example, x n t and x n some 2 over 3t, actually, you will learn the decimation and interpolation or upsampling and downsampling. This can be done actually easily by multi-rate signal processing, not like this one. Okay, but you have if this strange ratio not can be represented by a rational number, because root 3, square root 3 cannot be a rational number, right? As you learned in 수학의 정석, right? You try to prove that, probably square root 2, but anyway. Now, this is very interesting. As a communication engineering student, I saw some filter like this. So we had an antenna and saw filter. What the filter? What does that mean, right? And actually, it meant surface acoustic wave. 표면 음향파 filter. And it was a little bit bulky. with some SMA connectors like this size. And it was very cheap. And there were very good specifications like, okay, stop band, pass band, something like that. And I had no idea about what is surface acoustic wave filter. And eventually I learned that this is something like you wanted to do analog signal processing, filtering of the original incoming signal, and you mimic the processing as a discrete time filter by converting RF signal. So RF signal is what? Radio frequency wave, right? This signal to electrical signal, this and acoustic signal, sound signal. And what happened? Sound signal propagates through a media much more slowly than the radio wave or electric or magnetic field. So they designed some gate that accepts vibration gate so that they had a filter. So this is the idea. And another one is just for interfacing the laser or optical signal with the electrical system. In our network switches of the internet, what happens? We use fiber optic cable where not the radio wave, but the laser generated photons move forwards and backwards, right? So before, we had very bulky, large-sized converters. But these days, these converters become smaller and smaller. And people have sometimes found that computation can be done not in electrical component, but in fiber optic component. So there are some physics professors who does research on what? Using lasers and mirrors and prisms miniaturized and other things to implement neural network. And they say that in some cases, not always, but in some cases, using these things has much more advantage than electrical electronic circuits. Fiber optic something is much better. So what do we need? We need to convert the electrical signal to photon and then all analog mirrors and something and lenses, right? And we eventually will convert the signal back to the electrical signal, especially digital signal. Got it? And also, yeah, I talked about that. Also in communication simulations, we have the problem. For example, when I did some project, I had to show that my channel estimator really works very well. The problem is that at that time, the channel emulators are very expensive. What, like, how many? Some one, and I couldn't buy. So I purchased the 100-meter cable, pairs of, and make their lengths different. And what? I used the RF splitters and combiners. And if you remember correctly, 1 microsecond in free space corresponds to the propagation length of 300 meters. So 100-meter cable, because the speed of light is faster than speed of propagation through cable, so may correspond to what? Around, for example, 300 meters free space, which may induce you multipass difference 1 microsecond. So my student had cables and splitters and combiners put together and measure the channel response using the vector network analyzer. And then we also used our channel estimator and draw the channel response and said, perfect, something like that. And this is not exactly the corresponds to this idea, but it's very similar. So what I want to give you is not just read this section and this sample application of what you learned, but remember this one. Sometimes we boldly convert our electrical signal to something else. Never hesitate, okay? Never confine yourself in electrical circuits. Sometimes you just go out of it. Use lasers or something else, strange thing, I don't know, okay? And then come back, because anyway, we need electronic circuits to process, visualize, and everything. Okay, time's almost up, and it seems I have something still missing. Let me see. Yeah, anyway, those things will be covered in the next class meeting. Okay, that's all for today.